Illuminated by IEEE Photonics is a podcast series that shines light on the hot topics in photonics and the subject matter experts advancing technology forward.
Hi everyone, and welcome to today's episode of Illuminated. I am Akhil, and as the Associate Vice President of the Young Professionals and the Chair of the Young Professionals Advisory Committee, it is my pleasure to be your host today. I'm a biomedical physicist working at the University of Glasgow as a Leavyhume Earlier Career Fellow. In my role as the at the IEEE Photonics Society, I'm supporting and promoting initiatives, very much like this podcast, to raise the profile of the valuable young professionals within various sectors. The Young Professionals Initiative is for graduate students, postdoctoral candidates, and early career professionals up to about 15 years post their first degree. This affinity group within the IEEE Photonics Society is committed to helping one pursue a career in photonics. We're here to help with 1. Evaluate your career goals, 2. Better understand technical pathways and subject matters, 3. Refine and improve your skills, and 4. Grow your professional networks through mentorship programs and all the other exciting initiatives that you can find on the website. Now, on to our podcast. In this podcast, we're going to discuss nanophotonics with our special guest Deep Jariwala from University of Pennsylvania and Lorenzo Pavesi from University of Trento. In today's episode, you will hear from Deep as we discuss nanophotonics, his journey through Northwestern University to now as faculty of University of Philadelphia. We go beyond academia with career and research advice from Deep. There is something for everyone today. It is now my pleasure to introduce Lorenzo, who's serving as the chair of the Society's Emerging Technologies Task Force. The IEEE Photonics Society's Emerging Technologies Task Force is responsible for identifying, devising, and cultivating new technology directions, recommending new programs that focus on the leading technologies, the cutting edge of photonics sciences, and promoting technical activities in support of both academia and industry for the Society. Lorenzo Pavesi is a professor of experimental physics at the Department of Physics of the University of Trento. He leads the Nanoscience Laboratory and is the director of Q@TN, a joint lab between the university, the Bruno Kessler Foundation, CNR, and INFN. He was the first president and the founder of the IEEE Italian chapter of nanotechnology. He has supervised many PhD students, many master's theses within his research focus of integrated quantum photonics and neuromorphic photonics. In silicon photonics, he is one of the worldwide recognized experts. He's an ERC grantee. He is an author or co-author of more than 500 papers, editor of more than 15 books, author of 2 books, and holds 9 patents. He is the chief specialty editor of the section Optics and Photonics of Frontiers in Physics and the founding editor of the series Photonic Materials and Applications, a joint initiative of SPIE and Elsevier. In 2010 and 2011, he was elected Distinguished Speaker of the IEEE Photonics Society. He's a Fellow of the IEEE, SPIE, of AAIA, and of the SIF, and now serves within the IEEE Photonics Society as the chair of the Emerging Technologies Task Force. Over to you, Lorenzo.
Thanks, Akhil. So it's really a pleasure to be here within this podcast. So I would like briefly to introduce the topic of the today podcast, and then I have the pleasure to introduce Professor Jariwala. So nanophotonics is an interdisciplinary field that combines nanotechnology with optics to study and control light on or at the nanoscale. Nanophotonics could be further classified into studying optical properties of nanometer scale materials and structures, or designing and making structures that confine and manipulate photons in nanoscopic dimensions. It involves the use of nanostructured materials and components to manipulate the behavior of light, such as its intensity, polarization, wavelength, or direction. Application of nanophotonics range from telecommunication to medical imaging, from quantum technologies to semiconductors. Research in this field is advancing rapidly, leading to new possibilities for the development of nanoscale optical components and devices, as well as the potential for new materials and processes to enable new applications. Today we talk about nanophotonics with one of the most important young researcher in the field. And therefore it is my pleasure to introduce Professor Deep Jariwala of University of Pennsylvania. So Deep is an assistant professor in the Department of Electrical and System Engineering at the University of Pennsylvania. Deep completed his undergraduate degree in metallurgic engineering from the Indian Institute of Technology, Banaras Hindu University, and his PhD in material science and engineering at Northwestern University. Deep was a Resnick Prize postdoctoral fellow at Caltech before joining University of Pennsylvania to start his own research group. His research interests broadly lie at the intersection of new materials, surface science, and solid-state devices for computing, optoelectronics, and energy harvesting applications. In addition to the development of correlated and functional imaging techniques. Deep research has been widely recognized with several awards from professional societies, funding bodies, industries, as well as private foundations. The most notable ones being the IEEE Photonics Society Young Investigator Award, the IEEE Nanotechnology Council Young Investigator Award, the UPAP Early Career Scientist Prize in Semiconductors, the Alfred Peter Sloan Fellowship, and also the Bell Labs Prize. He has published over 100 journal papers with more than 60,000 citations and all several patents. He also serves as an associate editor for IEEE Photonics Technology Letters. So, let me talk with Deep now. So I would like to introduce and start by asking Deep to share with us how he chose the field of nanophotonics.
Thank you. Thank you so much for the very kind introduction. It's really my pleasure to be here and talking about nanophotonics today. And I would like to say that IEEE as a society has been very, very instrumental in guiding me into nanophotonics. So my path into nanophotonics was somewhat different than what many researchers or many young researchers that I see today taking. Many of the researchers I see, they are introduced to nanophotonics quite early on in their careers. I was introduced to the field of photonics and optics quite late during my postdoctoral work at Caltech. One of the things that I was interested in was to look at how light interacts with atomically thin or very, very thin semiconductors. And these are semiconductors that I was studying during my PhD, but for purely electronic devices. But then they also have very interesting optical properties. And so, as part of my postdoctoral work, we started looking at that. And that is where I first got interested that, not only is a simple light interaction with these semiconductors interesting, but also if you can make them into interesting nanofabricated structures via all kinds of micro and nanofabrication techniques, you could introduce more exotic effects of light being trapped in them. And that gave birth to a very interesting idea, which is, can you really make viable solar cells that are just a few nanometers in thickness? And how can you do that? So that was a question that quite fascinated me, that you could make a fully functional and fairly efficient solar cell, which was 10 times smaller or 10 times thinner than the wavelength of or average wavelengths of sunlight. And I was quite fascinated by that, and kept studying further and further, and eventually now my interests into nanophotonics are into all kinds of applications.
Oh, that's very interesting. And nowadays, what are the topics that your group is working on, or which kind of technology are you interested in nowadays?
Yeah, so this is also quite a important question. My early interest in these very thin semiconductors has continued over into our independent research here at UPenn. One of the class of nanophotonic, nano optical materials that we are very interested in studying are excitonic semiconductors. These are similar to most semiconductors that we know of, but because they are from the structural level, they are quite confined, right? So I think many of us in the community may be aware of, and Professor Pavesi and other have worked on the 3-5 materials or silicon-based quantum well structures. Quantum wells are a very well-developed technology at this point. They are into many sort of internet communications as well as lasers application. But now we have this class of materials which are called two-dimensional materials or van der Waals materials, which naturally occur in this quantum well-like structure or layered structure. What this allows you to do is, even at room temperature, there are very interesting optical properties that emerge from these materials, which is strongly bound excitons, right? So they have very resonant absorption of light. What this leads to is very interesting effects, such as light resonates or interacts with this material extremely strongly. So then if you make structures out of these materials, you can manipulate light. And manipulating light using these materials is much more easy than, for example, three-dimensional materials like silicon, for example, just because these materials are very thin. So if you apply electrodes on them and apply voltages, you can change their optical properties. You can change their absorption, their refractive index by large amounts. 30-40% modulation of refractive index you can get by application of voltages. This is actually much, much more different than, for example, silicon, which has less than a percent of change in the refractive index as you apply voltages. And so this gives you a huge knob to tune the properties of the light dynamically with the voltage as the light interacts with it. And so this has got us very excited. Early on, this we were limited in terms of the size of these materials because they were available as very tiny crystals. But nowadays, our group can grow these on entire wafers. So it's becoming like a wafer scale technology. So that is one of the reasons we are still working on these materials. And the key application we are trying to look at is see if you can make metamaterials out of these. Right. So using excitons as the resonance within these materials, can you make a whole new class of metamaterials, which we call as excitonic metamaterials? And more importantly, then, can you, by application of voltages, tune the dispersion or optical dispersion properties of this artificially made excitonic metamaterial? And this could have applications in all kinds of things, all the way from things like excitonic lasers or polaritonic lasers to optical modulators. Of course, photovoltaics is still of interest because they absorb so strongly in the visible part of the spectrum. And then we are also interested in, using these kind of materials to guide light on the chips for communication between different devices, or what is popularly known as electronic photonic integration for micro and nano electronics. So these are sort of the areas we're looking at.
So, according to you, so what are the nowadays challenge in the fields of nanophotonics? So, do you think that a sort of hybrid approach where one merged nanophotonics with standard photonics is viable, or so? Try to
Yeah,
share with us your ideas about that.
sure. Sure. This is again extremely important question. Photonics as a field has been around for a few decades now, and there are of course some really mature technologies, right? Silicon technology, silicon nitride based technology, even indium phosphide based photonics. All these are quite mature. And then there are these new and emerging materials coming around. And one challenge that has always been there is how do you confine light into smaller and smaller dimensions, right? And when the idea of plasmons or plasmonics came around, it was quite exciting that by using nanoscale metals or nanometer scale structures of metals, you could really confine light down to even just a few nanometers, right? In terms of the mode volumes. And so that got people very excited, but it comes at a price. The price that most of these things typically come at is that in more loss, right? You lose the light to more electronic scattering, rather, and therefore the energy dissipation is large. So this trade-off has always been there in photonics. Should we stick to our classical or standard materials that have been used in photonics, where you will hit a limitation in how much you are able to shrink the light, Or do you go to newer materials which allow you better functions such as confining light further down below and ability to tune the light better and things like that? I think, and as Professor Pavesi indicated, a hybrid approach is better, right? Because one is you will be able to get best of both worlds, right? So that's actually interesting, and that will actually expand the application of photonics way more than what currently silicon or silicon nitride or indium phosphide based photonics can give you. The challenge, however, is the following: all of these newer materials, right? They are still nascent in the sense they are not as mature in terms of quality, purity, optical qualities, scaling up, fabrication and integration processes worked out in foundries, for example. So it may take a couple of decades for some of these newer materials to sort of mature. These excitonic 2D materials, or you could even say like lithium niobate and some of these other aluminum nitride based materials that are piezoelectric or ferroelectric, that may want to that have very high optical nonlinearities, which could be integrated into the nanophotonics. All of these materials will take, I think, at least a decade to mature further. And ultimately, hybrid nanophotonics would be the way to go, because it will not only allow you to have light sources on the chip, but also then extremely small waveguides and extremely tunable waveguides. And so what we can do with electronics now should be possible to do with photonics in the future if there is a sustained development in the quality, scaling, and fabrication integration processes of these newer materials.
And do you see a possibility to use your approach for quantum science and technology? Is there any enabling application where you think that nanophotonics can play a crucial role there?
I think yes. I think quantum science is I would say the frontier science right now, right? And everybody knows that the next big revolution in information science and technology will come from quantum technologies. The question is, which quantum technology ends up dominating, right? If you look at, for example, superconducting electronics or superconducting qubits technology, much of those operates in the microwave regime, right? And so the scope for nano or nanoscale confinement over there is much smaller. But if you look at quantum photonics in the visible to telecom range, certainly nanophotonics is going to play a huge role in it. Why? Because we need light sources, quantum light sources, which are highly pure, highly efficient, and highly bright, right? And they are also they should also be tunable. And all of these properties into quantum light sources are only going to come from these nanoscale materials and their confinement or their integration into novel optical nanocavities. They could be plasmonic cavities, they could be simple photonic crystal cavities. I don't know. I think the verdict is still out there, but I think it's going to play a huge role. And some of the materials that we work with, they're actually quite interesting in this regard, although still far less mature than, for example, say, indium arsenide or 3,5 quantum dots, which are much more mature in terms of quantum light sources. But very few materials exist which have high optical nonlinearities, can also host single photon emitters, and have high index and are highly tunable, right? I think some of these two-dimensional materials that we are working with have all these properties combined in the same material class. And I think that's what makes them interesting, to not only study them for basic quantum emission applications, but also thinking about making nanophotonic structures out of them to have a full quantum nanophotonic circuitry someday from these kinds of materials.
So do you think that there is a huge open field both for basic science as well as for potential application of nanophotonics?
Yes, you're absolutely correct. Yeah, there is, I think, opportunities in both spaces. On the basic science, I would say, the opportunities are more about developing the materials and discovery of new property of the materials, right? That's where the approach is on the basic science side. On the applied side, I think the opportunity has to be more in terms of uh, scaling of the material group and device fabrication. I think one challenge that people have seen and I should have highlighted this earlier too, that whenever a new material comes, right, there's a lot of excitement, a lot of basic science happens, a lot of research happens. But as you start talking to the industry, and as you start thinking about how would we integrate this in a microfabrication foundry or an actual product, all kinds of challenges come up, right? And then like there's one example of this quite recently, and many of you may be aware of it, lithium niobate. Lithium niobate is another extremely promising material for nonlinear photonics, and now people are using nanoscale resonators of that in nanophotonics too. But lithium is terrible for silicon CMOS foundry. So getting it into like an industrially compatible processes that can survive all the fabrication steps, does not contaminate everything else. There is large stability of these materials over long time scale of operation under extreme conditions and so on. All these things have to be worked out. And so I think this is where people have to uh, be careful, right? The basic science, of course, is extremely exciting, but you need a set of engineers too who can connect the basic science to what is possible in technology versus what is not.
So I think that this is a good moment for Akhil to jump in, and maybe you can ask and chat with Deep.
Excellent. Thank you very much, Lorenzo. That was incredibly interesting. I've got so many questions and so many things to sort of point out, but I'm going to start with with one question regarding the work that you do, Deep, and after that, I have a few questions from a young professional's perspective as well. And I've asked this question to quite a few professors, so I'm going to put you on the spot in a second. Now, of your experience and everything that you have done up until now, can you sort of remember or recollect if you've got one or maybe two papers that you wish you had written? Something that's incredibly important in your field, but a paper that you wish you wrote from a long time ago, or even
Okay.
now.
Yeah. Okay. So, I have multiple answers to this question. I hope. So, personally, yeah, I work in the field of two-dimensional materials. It would have been amazing to be associated with the early papers on the discovery of graphene itself, graphene's optical or graphene's properties in general, both optical and electronic. But more from a nanophotonics perspective, given the kind of research that is happening these days and some of the old literature that I go and read, 20, 30, even literature before I was born sometimes, right, to write review papers or get a full in-depth understanding of the field. I think the early papers on electro-optic effects of 3-5 quantum wells, right? These were works that were done by David Miller and others when they were at Bell Labs. This was the time before I was born. I think it would have been amazing to be associated with those kind of works. That kind of works ultimately led to the technology of modern telecommunications and modern internet. And so, being part of those kind of discoveries would have been very fulfilling, I would say.
I think that's incredibly interesting because what has happened here around the research lab that I work in as well has pioneered some of the optical tweezers research. And I always sort of look at those papers and I wish I was involved with that research back in the day. And then, of course, we had the Nobel Prize. And then now I'm reading quantum science papers. And then Anton Zeilinger and his research got recognized in the Nobel Prize last year as well. So I find that question very, very intriguing because you read papers and you always wonder, I wish I've written that one. So I've just got a couple of questions of my own, and I'm sort of wondering, for students who are sort of looking to move towards nanophotonics research and try and understand what's happening in the nanophotonics industry, would you happen to have any advice for them?
Yeah, sure. So I think as students, you should be have general advice for students, which is be curious, be inquisitive. But also, I think these days it's very important to know that our world is overloaded with information. So staying on top of things is sort of important. Like at least you should know like what is generally going around. But then within your own field or within your area of interest, try and get the best information possible. And in this case, whether you do it by yourself or have a mentor, a senior colleague, or a senior professor or senior student in the lab who can help you point to the right directions or right sources for reading about things. That would be wonderful. Um, but from an industrial perspective, we want to then you want to orient yourself, or the students want to orient themselves, whether you want to study nanophotonics more from a fundamental aspect or more from an applied aspect, right? Because industries are definitely our industries have much more narrow interests in nanophotonics, things they can make technology out of, right? And so for example, silicon nanophotonics is a very well mature technology. There are foundries doing these things. And for other types of materials, they may not find a pathway directly into industry. But that doesn't stop students who are working on optical materials or nanophotonic materials and devices in the lab to joining those industries. The question really is, what skills are you going to acquire that will help you guide your transition to the industry? And those skills are actually quite common throughout all the labs. You know, the kind of because the basic physics doesn't change, right? The kind of optical modeling that people do, like FDTD modeling or finite element modeling that you would do in the lab, that is pretty much standard. It's used all the way everywhere in the industry too. And so yeah, I think cultivating interest early on, finding the right sources of information to get interested in or develop knowledge in, and then making the relevant connection, whether to industry or to academia, would be my strong advice.
I think that's really, really, really good advice because in many, many cases, graduating students can use a subset of the skills that they have to build a career path. And that transferable skills, either academic or even the skills that they gain working with colleagues and all of that is very, very valuable. I'm almost thinking that you have my notes in front of you because that leads me to my next question very, very easily. You've supervised many students, you've got a substantial research group. What do you think about mentorship and the value of that in an academic environment, in a career environment? What do you think the responsibilities are?
Yeah, so this is again quite important but loaded question. Let me try and answer some of the effects or importance that mentorship has had in my own career, and then I could probably give some advice on how on the upcoming generation of students. I would say mentorship was extremely important in my own career. Even though I was a young scientist who wanted to do things mostly by myself, I got very good mentorship in the form of both PhD and postdoctoral advisors. They not only sort of directed me in the proper direction in terms of the research topics, but cultivating me on how academic world is, how the industry world is, or how the professional world is in general, and what are the skills I should be developing, both technical as well as interpersonal. Because as you move further and further in career, just technical skills are not the most important skills. You know, the interpersonal skills, how to write grants, how to interact with other faculty or with funding agencies or at conferences, or how to mentor students, right? All these is extremely important. And I was introduced to these things early on. So when I was a senior graduate student, I was actually assigned first year graduate students to mentor. So I became their day-to-day mentor. And this was possible in the groups I was in because these were large groups, 30 people, 40 people groups, right? And so basically you were sort of the senior graduate students or postdocs were mentoring junior graduate students. And so you sort of get on a day-to-day basis how to work with other students, how to cultivate interests of younger generation of students into your area of research and see what type of skills they pick up, or what things work, what things don't work in terms of teaching them about or passing on your knowledge to them. Similarly, when I was a postdoc, this was very handy because my postdoc group was also very large, and so we were essentially asked to sort of mentor and work with a few younger graduate students. It was extremely helpful in that sense. So getting exposed to not just the technical side, but the non-technical sides of the job, whether it's academic or industry, I think is extremely important. From all these things, what I have learned and tried to incorporate in my group is that there are some very basic or fundamental things that sort of apply to all students in terms of mentorship, which is you have to give them their intellectual freedom. At least that is what I have found. So I try to give intellectual freedom to the students and try to tinker their thinking or approach by asking them like questions, hard questions about the kind of things they're trying to do in the lab. If you try to box people into a very narrow area and tell them to achieve or predefine the goal for them, that's not ideal, at least in the academic research environment. So leaving them, a little bit open to explore, and also more importantly, open to collaboration, not just within your group, but also with other external groups, is actually quite important. The other thing you can expose students to early on, which actually helps a lot in mentorship and career development, is sending them to conferences and asking them to not just see other talks at conferences, but also network at conferences. That opens up their mind to a variety of new ideas, variety of new possibilities. And so if you inculcate these things early on, I've generally found, again, I'm still early in my career, but I have found that it leads to students being well trained in all aspects of professional life, right? Whether it is that they want to go into academia later or they want to go into an industry later, it doesn't matter. I have had students who have found internships while going to, in companies while going to conferences, and then those internships have led to job offers. At the same time, I have found that I have had students who have just talked to some professor at a conference, came back, we initiated a collaboration, and that ultimately led to a postdoc offer. So it works in every direction. And having this open mind and asking the students to be inquisitive and be collaborative, I think is really important.
I think that's very, very interesting because I've started to do this with some of my students as well. Every time a student of mine goes to a conference, I give them a little sheet of paper and it says on top, three people I met, three things I learned, and three things that I'm very, very interested in. And they come back with that sort of predefined template, and we sort of go, okay, you spoke to these people, what did they do? You went to a random conference presentation and you found it very interesting. And what do you think you can learn from that? It sort of makes it an interactive process. This leads me very, very interestingly. It's a way of asking a similar question I've already asked you, but maybe we can look at it from a different perspective. Now, most students who are graduating right now are incredibly capable, incredibly intelligent. They love what they do and they're graduating with degrees. But they're going out into a professional and a scientific climate that is ever evolving. It could be great today, it could be challenging tomorrow. What do you think, besides academia, are the skills that students should develop? What do you think they should arm themselves with so that they can be desirable as researchers outside of academic skills?
Right. So, academic skills versus non-academic skills there are overlapping skills, but then there are non-overlapping as well. I think when you think about careers outside of academia, I hate to say this, but slowly they are becoming more and more rewarding, right? I mean, in industries, startups are all over the place, and they are making very good headway progress in a lot of emerging technologies. But I think one of the skills that or things that students need to recognize when they step outside an academic environment in terms of their careers or career development is that the impact at a technology level on society matters a lot more than having a really cool and interesting piece of data that explains new science. I think a lot of times when students, especially PhD students and postdoc, they have stayed so long in the academic environment that sometimes it leads to a bubble-like mentality, which is, oh, look at this really cool, neat piece of data and all the wonderful science that is behind it, right? But that does not mean too much if
there is no pathway for taking it towards an actual scalable commercial level technology. So when you go out there in a non-academic environment, setting your mindset up to go from a scientific impact to a societal or technology impact of your research project or of your vision is extremely important. And once you orient yourself to that, and that becomes your main goal, I think adjusting to an industry environment becomes much easier, right? Then, of course, there are all other non-technical aspects such as networking with people, and then asking the right questions at the right time, and being professional about your work setting and everything. That all is just built in. But I think the mindset orientation is the most important thing.
Thank you very much. That's very interesting because we all sort of go out into the research environment, and the skills that we actually need are quite different from the ones that we acquire in the lab itself. So this is a bit of a curiosity question as well as something I'm personally interested in. I'm originally from India. I've made my way through graduation and degrees through India, then through Europe, and now in Glasgow for my postdoc and my fellowship. You have had a similar transition as well. How have you found moving both geographically and through academic roles? What is, say, the good side of it and the challenges that you have faced along the way?
Right. So I think I only mostly have positive things to say about this, because going through different geographies and also different scientific fields, or scientific disciplines, has only enriched my experience as a researcher. The way of doing science is different in different countries or even at different universities in the US. And the way of doing research is also different across different disciplines. Like materials and electronics people look at the research in a slightly different way than the photonics people, right? And so this has only enriched my experience. And the best thing I've benefited from this is that I'm able to connect missing pieces in two different fields. And this is something that is truly rewarding as an independent researcher, because you see things that are missing in one big domain of science, and then you see missing in the other big domain of science, and you can find the link between them because you are among the very few people who have actually studied both fields in great detail. So that has been the great part. From a non-technical side, I think you learn interesting and positive things from different cultures, right? For example, the way of doing science and just general way of life of American culture is very different than in Indian culture, right? And so it only enriched my experience in sort of modifying certain ways of working, certain ways of social interactions, and things like that. So it was all very positive for me overall. The highly collaborative nature of American science has been very positive impact too on me, and that is something that I've adopted throughout my research group and mentoring style here as well. Of course, there will be some misunderstandings when you first transition, right, to any place, whether it's geography or within the same country to a different university or a different discipline. The people won't understand the jargon, or people won't understand the styles of working. But I think eventually everybody gets used to it, and it only leads to a positive enrichment of any scientist.
That is so incredibly true. And I find that so relatable. As you can obviously understand, I'm nodding my head and agreeing with every single thing that you're talking about in terms of that transition as well. That's very, very interesting. So you've been working with professional societies, you've been working with the IEEE for a while. I'm sort of started to get an idea of when did you start doing this and how has that affected or influenced or supported your career progression?
I was associated with the IEEE even as a graduate student, even though my degrees were mainly in material science and engineering. But then, since I became a faculty, I actually started participating in the local IEEE chapters over here in the Philadelphia, Delaware Valley area. And that's where I got to learn more about volunteering for IEEE. So I joined the Young Professionals Committee of IEEE, the EDS Optoelectronics Committee. Then I have very great colleagues in the department who have been associated with IEEE Photonics Society for a very long time, decades now. And so they introduced me to IEEE Photonics Society conferences and encouraged me to go to that. And so that sort of started developing the interest slowly. And then when I started going to conferences, they started inviting me to other and networking with other IEEE senior professionals at the conference. They started inviting me to serve on other IEEE committees or society committees. And then that sort of work I started enjoying, at least in the time that I could find. Of course, you cannot find time for doing all service work, but at least the work that I was involved in, I found great joy in serving for that committee work. And so that kept extending. And most recently, the way I've been contributing, and I find this to be also quite rewarding, is serving as associate editor of IEEE Photonics Technology Letters. I've always wondered, when you submit your research paper, it gets reviewed and comes back, what actually goes on the other side? And now that I am on the other side, I get to see this firsthand as papers come in, how you evaluate them, how do you pick the reviewers, what kind of reviews come in, and go through the whole process. And I feel privileged in some sense of doing that because you want to give back to the society. It's very important. And you are often thankful when people are reading and reviewing your papers. And so you helping other people or do that for other people's papers or other papers of other community members and doing it in a fair way and helping them get their work out there is quite rewarding to me personally.
That's quite interesting because I'm on the same side of that curiosity as well. Because I've submitted many a paper, I'm helping my students submit their papers for research as well, and I wonder about the peer review process. So I'm probably going to get in touch with you afterwards. Tell me all the details, and if there's something that you can't talk about in the podcast, I want to know that as well. So in your experience then, from all of the work that you have done, all of the things that you have led, been a part of as well, if you had to talk about one of the most important leadership lessons you have learned, what would that be?
Yeah, I think in terms of leadership, it slightly feeds into some of the things I said earlier. But enabling people, enabling younger students, for example, or anyone, it could be more senior team members too, in achieving what they want to achieve by understanding their goals rather than imposing your ideas or your vision
Yeah.
very narrowly on them is probably the most important lesson I've learned. Or not lesson, but over the years I've seen that that is the most effective way is to understand what your mentees or your group members or your team members want and try to make the circumstances such that they are motivated and they have the resources to achieve those goals. And that's been my sort of like overlying principle to operate the group as well.
I find it very encouraging that although there are so many ways of doing mentorship and leadership roles and positions, some of the good things are always the same. Some of my professors in the past, and I've taken their techniques now to do the same. It's very interesting when you ask a PhD student or a project student, the first question being, do you want to stay in academia or do you want to go to industry? And that itself defines how you supervise that student because if they want to go into industry, you give them the skills that they need in industry. If you want them to go into academia, then you give them the skills to go to academia. And that sort of shapes the way you supervise a student. Because at the end of the day, each student needs to be supervised the way they need to be. There's no one stop shop for everything.
Yeah, and I think it also dictates then what type of projects you assign to them, right?
Exactly.
Because sometimes there are really fundamental projects which may have very limited skill set that may be applicable to industry. And a student who wants to go to industry may not be the best fit for that project then. So it's
Exactly. Exactly. I have a couple more questions regarding early stages of careers. So if you had to give somebody, I mean, another way of looking at the question is if you had to go back to your younger self and give yourself one advice when you were just finishing a PhD and you were on that point of your career where you could have gone to industry, you could have gone to academia, but you've just finished a degree. To somebody like that or your younger version, what advice would you give?
I think one of the things I would have done more is taken more classes in outside my discipline,
Yep,
right?
absolutely.
And educated myself more in other areas of research, particularly from a theoretical perspective.
Mm-hmm.
right? Like I regret not taking more physics classes to understand more quantum physics, for
Mm-hmm.
example, right? I think people would say nobody understands quantum ever, right? But yeah, I would have really appreciated more quantum classes, for example. I would have benefited taking a little bit, maybe even one class, an introductory class on information theory or
Yep.
the information side of computing. Yeah, and these things sometimes I regret now because I'm into large collaborations where people
Yep.
are talking about these areas and I have limited understanding. So getting myself more educated when I was a student or in my student days would have been better.
It's very interesting you say that because I, as a physicist, now wonder I wish I'd taken more engineering classes so I understand how these things are made. And don't worry, Lorenzo, I haven't forgotten about you. I'm going to ask you the same question again in the final thoughts, just in a few questions in a few minutes. So you have a question to prepare for towards the end. So just building on that, Deep, how important is it, do you think, to diversify your research experience, your skills, your expertise? Or do you think on the flip side of that, do you think it's really, really valuable to become incredibly good at one narrow topic? I know these things change as you go through academic careers because first it's about the research that you do, then it becomes grant writing and paper writing skills, and then people skills. But as an early career scientist, do you think it's really, really good to be amazing at one thing, or do you think it would be good to be good at everything? Obviously, these comes with its own challenges.
Yeah. So again, this is a great question, and I think there is no one answer to this question. I think it will really depend on who the person is, what is their field, and so on, right? I personally am a scientist who likes to like explore every area where my interest is. So I would just, I when I launched my research group, I was applying to any and every grant call where I had something interesting to propose, like
Hmm.
without even thinking whether how good of a fit I was and whether I would get rejected or even considered for that grant call. Now, that of course had its challenges, and I had a hard time focusing and getting grants early on to get started. But eventually everything worked, and now I have a significant size group which I have a hard time managing, right? But it's fun in its own way. The advantage I have seen in this kind of approach of being somewhat broad in research interests and spread out is you will never be short of resources to maintain sort of a healthy size research group and research productivity, right?
Yep.
But the downside of it is, of course, very obvious, is you will always be distracted into multiple things.
Hmm.
The converse approach is that you really are focused on solving just one singular problem, right? And all in you go into that one single problem. And the problem with that approach, I would first highlight the problem, is it's risky,
Yep.
right?
Yep.
And the chances of you succeeding over there may not be 100%. What if there is competition there, right? And if you're not the most successful person in that area, maybe that negatively affects your career. But on the flip side, if you're successful over there, I mean, you start the field, you go on to become the leader in the field, so to speak, right? So, so that's sort of the up and down. There is also another risk that is associated with that kind of an approach. As you were saying, research fields evolve.
Hmm.
There
Yep.
are there are cycles in funding, right? I mean, everybody says this. Quantum science used to be a big deal when the first trapped atoms and trapped ion research started. Then there was a full lull in it, and now it is, come up again. What if you go through those cycles? Is your lab, is your research, is your group going to survive those kind of cycles if you are really focused into one area, right? So these are things to sort of be mindful of as you pick it. My personal advice as an early career person is that be in more than one area, because these days things change very quickly, right? Research fields come and go at a very fast pace because the human technological progress and human scientific progress, or our progress as a society, is much more fast, or the curve is only accelerating more as time goes by. And so putting all your eggs into one basket as an early career researcher has more risks than rewards these days, particularly.
I think that's very, very true. And it's something that I have had many a conversation about with my students as well, where I've tried to sort of break down that image of being a multitasker, where I basically have told my students, do different things, but don't do everything at the same time. If you do multiple things through the course of a day, a week, a month, that'll still help your career, as if instead of trying to do everything at the same time and not be good at anything. So I think it's one of those things where you have to be good at multiple things in order to be successful, but you can build those skill sets over a long period of time. It doesn't have to be now.
Yeah.
So my
Also,
last question, sorry,
I
go
should
ahead.
I should add over here that you also reduce the risk if you start with multiple fields as an
Hmm.
early career,
Hmm.
because you don't know in which field you're going to get success in. But then later on, as you mature in your career, you know one field is maybe going better than the other field.
Yep.
You can take that approach of going singular all in into one field and becoming the world leading expert over there, right? You don't rule out that option. But if you start with just one field and stay hold into that field for a very long time, it gets difficult for the scientific community, the funding agencies, whatever, to convince them once you are, no longer considered a young scientist or an early career person that, oh, I'm now going to certainly, take a diversion and go into another area. It is just becomes difficult to convince a large body of people of doing that, given that you have been in just one singular small field for like 10, 15 years. So this is why starting broader and then maybe narrowing down later in your career is a perfectly fair approach, I think.
It's interesting. In that way, you can even see the value of collaboration. If you find something very interesting, you can help with somebody else's research eventually to keep that connection going with different fields and then build up whenever you want to go and choose into one particular domain. So I have one last question before we go into final thoughts, both from yourself and from Lorenzo as well. If you're hiring someone, if you're looking at a young scientist, if you're, say, on a grant panel, and now in your role as an editor as well, what are the key qualities that you're looking at when you look at young scientists so that they can be successful in today's research culture?
When I try to look for students, a lot of people try to focus on grades and things like that. I'm just looking for enthusiasm, and the determination to work hard. I think if they understand these things, that one, you have to be passionate about and enthusiastic about the research subject, and two, no good outcome will come without a significant amount of effort. That's all. All other things can be taught, but these two main important things, which is the level of enthusiasm and interest or motivation, and true determination to actually work hard and achieve the results, you can't teach these easily.
That is so true. I'm going to send all of my students to you and you can give them the exact same advice. So, Lorenzo, I'm just going to bring you in for a couple of final thoughts, and I think we'll end with the final thoughts from Deep. So, a couple of questions for you, Lorenzo. The same question I just asked Deep. What do you think are the key skills or the key attributes or qualities you're looking for in young researchers?
Yeah, I'm essentially giving the same answer as Deep. So the passion, the motivation, the pleasure to work in this field. So this is the most important things. And then what I also typically consider are the soft skills of the potential candidates. So I need people that are able to play a role in a group. So they should be able to interact with each other. They should be able to communicate. They should be respectful, polite, but also they should be very, very effective in what they are doing. So those are also important because since we are running big groups, so we need people that are enjoying working together. So the a lone player is not someone who I am looking at.
I find it very interesting that no matter in both of your cases where you're leading giant research projects and big groups, and on the other end of the spectrum, me as an early career researcher, I'm working with one or two other researchers. The requirements that we're sort of interested in are still the same. We're looking for good people who like their job. I think it's very interesting that we're all looking for the same kind of people at every career stage. And my final question to you, Lorenzo, is if you could give any advice to your younger self, what would that be?
I would try to look for challenging problems. So I'm try to look for challenges, not to incremental research at the very early stage of your activity, meaning that, for example, deep here has a change in paradigm. So I grew up in a world that was saying that photonics is good, but typically the dimension of photonic device and photonics components should be large because of the wavelength of light. And so you cannot compete in terms of integration, increase of functionalities with electronics, because electronics, you have nanometer transistors, while photonics, so you have 100 micron optical fiber large, so that's big with respect to small. And here Deep has shown has a change in this paradigm, showing that in nanophotonics, so you can really play with nanometer structure and make light to do what you want to do by controlling materials and light matter interaction at such a small nanoscale. And so this was a big challenge. So all people were saying no, and Deep has shown us, and the people working in nanophotonics have shown us that yes, it is possible. So the advice is look for big challenge and try to give your contribution on this big challenge. So nowadays, artificial intelligence, energy, quantum, and other fields like that. So health, medicine, bioimaging, neuroscience, brain. So many big challenges. So try to be involved in those.
Thank you very much, Lorenzo. Thank you for that. So, Deep, any final thoughts?
No, I would just like to concur with Lorenzo over there that I think early on in your career, all early scientists, they should be unafraid and go after big problems, even if it seems really daunting. You have your whole life, whole career ahead of you. It wouldn't hurt spending 1 year, 2 year, or even more trying to figure out like the central problem in a big field and trying to solve it. And I would just add another thing on top of that, which Lorenzo pointed out, is there are big problems in every field. You may feel that, oh, this field is saturated, that field is saturated, what more I will contribute over here, but you will be surprised if you dig in. There are extremely challenging and really important problems in every single field, even in silicon microelectronics, which is at a 3 nanometer level. If you go and talk to the people over there, they will tell you there are extremely important challenging problems out there.
I think there's literally nothing more I can say beyond that. And I wanted to thank the both of you for your time. We've talked about an incredibly exciting, interdisciplinary, multidisciplinary field that spans so many applications, fundamental sciences. We've talked about electronics, photonics, quantum sciences, information sciences. It has been an absolute pleasure to talk to the both of you, and thank you so much for your time. Thank you so much for all the advice that you have shared for early career researchers. I have a lot of notes to take. I'm hoping for the recording to come out very quickly so that I can recap everything as well. So thank you so very much. And this is all I can say is cue the music.